Hello, in this video I'm going to be going over a past paper question involving friction. The question involves limiting equilibrium. If it's a single particle question, but with statics questions, things that are not moving, I would always first of all look to see if the equilibrium is limited and friction is involved, to see if it's limiting, because in some ways that makes things quite straightforward in the sense that we can just say that the friction, the model that we use, is F is equal to mu R, where R is the normal contact force, R is the reaction force, or also called the normal contact force. So we've got F equals mu R, and we're told that it's 1/5 in the question, so that must mean that F is equal to 1/5 R, which I'm going to mark on the diagram. Now the question here says it's on the point of moving up the plane, which is why on my diagram I've got it moving down. The friction, which always goes to opposed motion, is moving down the plane. So that's R over 5 there. Okay, so that's R, because it's on the point of moving up the plane, friction will be opposing that, so it's going down the plane. The other thing I should mention is I've written the weight in as 4.9. You might see it also, you might mark it as 0.5 G. The weight is equal to mg. So 0.5 G, but I've just gone straight for working that out. That's 4.9 newtons, because our default for G, unless stated otherwise, is 9.8. So that comes to 4.9 newtons. Okay, so that's all the forces on the diagram. We should now be ready to do our resolving. Let's resolve parallel first. This was a past paper question, by the way, and back then, it's from a few years back, looking at it was 10 marks. I'm not sure if it would be that now, but what would be the case is that a lot of the marks would be for your original equations. Back in this particular question, 3 marks were given for each equation, which seemed quite generous. I wonder whether that would be the case now. Either way, there are going to be quite a lot of marks early on, so make sure you take care, not only because you will get through the question more readily, but also because you will be, the marks are front loaded, so if things go wrong, you will get the majority later on. You'll get the majority of the marks anyway, because that's how mechanics is marked, probably maths in general, but definitely mechanics. Okay, so resolving parallel. Well, the one thing that's not going to come into it is the R. So that's because that's perpendicular to it. So we've got a component of T. Let's think about that first of all. That will have a component going up the plane there. Now we just have to decide whether that's T cos 20 or T sine 20. Well, it's T cos 20 in this case, because it's next to the 20-degree angle I've marked on the diagram. So it's T cos 20 there. Okay, so that's because it's marked next to the angle there, T cos 20. Okay, then we've got the component of the weight down the plane. The component of the weight, that's coming down here. Well, we've marked on the angle here 40 degrees here. So that angle's marked 40. We've got all this space here. So in that situation, it's going to be sine. So that's 4.9 sine 40 is the component of the weight. And of course, we've also got the friction, which is going exactly down the plane. Okay, so let's do our resolving equations. So we'll be ready to do that now. So we've got up the plane is T cos 20. Then we've got down the plane, they're both down the plane, we've got the friction and the component of the weight. So that's minus 4.9 sine 40 and minus r over 5 going down the plane equals 0. Okay, so that's the parallel plane. And say in the mark scheme I'm looking at, there's actually 4 marks already. 3 for the actual equation, and 1 for getting using F equals mu r. Probably the easiest question we'll normally find on a mechanics paper. So anyway, resolving perpendicularly. Now this time the friction, which is r over 5, won't come into that equation because it's parallel. But we've got r going exactly upwards. We've now got the component of t going this way, which will be t sine 20. Because of this space here, we've marked the angle here, and obviously we've got the 2 in the opposite direction anyway. So that's t in a perpendicular direction. So that will be t sine 20. And then we've got the component of the weight, this 4.9 Newton weight, which is next to the 40 degrees I've marked on the diagram. So that's 4.9 cos 40. Okay, so that's the component of forces, which should enable us to write our equation. So that gives us t sine 20 going out to the plane plus r going up the plane. They're both going in that direction, but going the opposite direction is the 4.9 cos 40. Equals 0. I say in the actual scheme I'm looking at, we've got 7 marks, but with that, but I suspect it might be more like 5 now. But still, 5 marks for getting our equations right, and then probably another 3 for actually solving it, which is actually going to be a bit more work, a bit fiddly. So we're going to substitute for r, because from this equation here, we've got r equals 4.9 cos 40 minus t sine 20. Okay, so we've got those two, so we can substitute for r. From that r, we can substitute into there. So we're going to substitute for r. Just taking care. So that's t cos. That's t cos 20 minus 4.9 sine 40 minus 1/5, taking the fraction outside, r, which is 4.9 cos 40 minus t sine 20. Oops, sorry about that. Equals to 0. Okay, so that's our equation. So that should enable us to, if we can rearrange that, we should be able to get a value of t. So bringing the t bits together, we get, and multiplying out, we got t cos 20 there. And when we times this by 1/5, being careful of the double negative there, that's going to be plus 1/5 of sine 20 t. Put the t in the middle of that. Okay, t. And then we've got the minus 4.9 sine 40. And then we've got the minus 1/5 times 4.9 cos 40 equals 0 from multiplying that out by the 1/5. Okay, let's take the t over to the other side. So we've got t cos 20. So let's factorise first and bring the t over to the other side. So we're factorising, taking the t out, so it's cos 20 plus 1/5 sine 20 then equals to 4.9 sine 40 plus 1/5 times 4.9 cos 40. Now I'm going to use the calculator. I didn't use it up to now because it can get a bit messy if we try and obviously using the memory it's possible to work these values out. But I'm going to put these use the calculator now. These bits, this bit here comes to 1.00809 blah blah blah, and this bit here comes to 3.90038 blah blah blah. So dividing the two, we'll get t equals to that 3.900 over 1.008. Make sure you use exact, or use the memory, or store them in some way so that we're not getting any inaccuracy. But to three significant figures, that's going to come to 3.87 newtons. Okay, so that's the first part of the question done. The second part, it would be it wouldn't be really much difference really if we were to do the second part, just that friction would be reversed. So instead of going through that in detail, what I might quickly do is just copy and paste what I've done and just see so quickly how the how that changes. So I'll just do that in a moment. Okay, so this part is now moving on the point of moving down the plane, so the friction reverses. So what I've done is, instead of going through the whole thing again, I've copied the question, copied the equations I've done, and it'd be useful to see how it changes. Obviously the components are the same, but friction's reversed, so this changes to plus here. It changes to plus. Okay, so that then, this equation doesn't change at all because friction is parallel to the plane that's perpendicular. So that's going to change this to plus here. Okay, so that changes that to plus, and so just some of the equations in the subsequent bit will change. So we've got t cos 20, and now it will be minus 1/5 t sine 20 for that, because it's now minus, but it will be minus 4.9 sine 40 minus 4.9 sine 40 plus 1/5 4.9 cos 40 equals 0. Taking that over to the other side and factorising out the t, so we've got t cos 20 minus 1/5 sine 20 equals to 4.9 sine 40 minus 1/5 times 4.9 cos 40. Right, so that's the calculations there. So that gives us t. This bit here comes to 0.8712 blah blah blah, and that equals to this bit here comes to 2.3989 blah blah blah. So t is equal to those two divided by each other, so that comes to 2.75 newtons. So which up the plane to stop it moving down the plane. Okay, to stop it moving from down the plane, we've got that's what we need to stop it doing that. So basically, in this situation, basically equilibrium exists if t is between those two, and these are the kind of limiting values in between. This is what limiting friction or limiting equilibrium happens on the boundary. So if t is less than 2.75, it'll move down the plane. If t is more than this, it'll move up the plane. And if t is in between, it stays in equilibrium. And the boundary is where it's in limiting equilibrium at the point where it would be equal to. Obviously, these are approximate, these are rounded answers, but hopefully you get the idea. There will be a particular point on the boundary where it's in limiting equilibrium. Okay, so that is that question finished, and hopefully that's useful. I said the question was 10 marks. I think it was only the first part that was 10 marks, and I think the second part has just been added on to the original question. Okay, so that's it, and we're going to be doing more resolving, and hopefully you're getting the idea of how important it is to get the original equations correct. Okay, hope you find it useful, and let's leave it there. If I can get off, bye.